So, well, can you hear me? Can you see me, please?
Yes. Yeah.
Okay.
Yes.
Welcome, everybody.
Hello.
Hi.
Buongiorno a tutti gli amici italiani che si stanno collegando in questo momento. Sto provvedendo ad accettare, come al solito, le ultime richieste. Benvenuti. Oggi è una giornata di cui sono molto contento, perché ho il piacere di ospitare una persona a me cara che ho scoperto quale eccellente docente proprio negli ultimi tempi, non lo conoscevo in questa veste, e quindi vi propongo un argomento molto interessante tramite le sue parole, la sua esperienza sull'effetto di Haas o effetto di precedenza, che ha un'importanza notevole nelle nostre installazioni audio, soprattutto in ambienti confinati, in ambienti altamente riverberanti. Nelle mie ricerche di questi ultimi anni ho capito quanto importante esso sia e come sia prioritario rispetto a tutte le altre variabili del tuning. Ho sperimentato anche sulla pelle di ignari fonici durante concerti in vari ambiti e contesti quanto la localizzazione dell'immagine sonora in abbinata al nostro modo di ascoltare, alla psicoacustica che caratterizza il nostro ascolto, sia la chiave vincente, la chiave di lettura vincente nel disegno e installazione di un efficace sistema di rinforzo sonoro. Ho scoperto che poi tra l'altro sono cose abbastanza note pure, insomma, ecco, le ho diciamo così verificate sul campo, come rispetto ad un sistema sonoro ben ottimizzato, ben equalizzato, ben allineato, tra virgolette, tra le sue singole parti, tra i suoi singoli sottosistemi, ma non ottimizzato per una corretta localizzazione dell'immagine sonora sul palco. Ed un sistema invece anche improvvisato, non eccelso nel tuning, nelle qualità di ascolto, ma ben localizzato, soprattutto in ambiente riverberante, o meglio ancora semi-riverberante, che sono la maggior parte degli ambienti con cui noi ci confrontiamo nelle ordinarie installazioni, sia la scelta vincente sia stato sempre quello, la seconda ipotesi, più gradito da parte e dell'audience e dei fonici front of house. Bene, abbiamo il piacere di parlare di effetto di Haas e quindi di effetto di precedenza con il caro amico Jason Romney. Welcome, Jason.
Thank you.
Hi, welcome. Per approfondimenti sull'effetto di Haas, sul quale ho scritto anche alcuni articoli sul mio blog Lato Oscuro della Fase, potete ecco, rileggervi questi articoli per ulteriori chiarimenti. Jason Romney è un esperto di musical, teatro, eccetera, quindi ha una lunga esperienza in questo settore e una lunga esperienza su queste tematiche ed è professore all'Università della North Carolina Scuola delle Arti. La chat sarà moderata, il webinar sarà moderato da Alberto Bonardi, Gianluigi Ferroni e Abe Shell. Invito pertanto, tacendomi, quindi non rubando ulteriore spazio, voglio essere molto breve quest'oggi, al mio ospite, invito Alberto Bonardi che ci introdurrà un po' sulle nozioni tecniche ed alcune informazioni basilari sullo svolgimento del webinar. Bene, buon webinar e ci vediamo dopo.
Hi, everybody. This is Alberto Bonardi, FOH and studio engineer. I'm just here to introduce the other two moderators of this webinar. We will have Gianluigi Ferroni from Italy and Abe Schill from Ireland. They will reply to your question. Gianluigi Ferroni, especially in the Zoom chat, and Abe in the Facebook page of Fedele. So before pass to Jason, let me introduce you to some basic concept that we have in this webinar. So I will, okay. So for who's not involved into live music or theater sound, so like many engineers, probably there's other people now following this webinar. So I can just explain briefly some of the terminology that Jason will use. So we refer to the positions on the stage from the point of view of the actor or the artist that stays on the stage. So we will talk about stage right and stage left. That will be the opposite from the audience view on the stage, and upstage and downstage, where downstage is closer to the audience and upstage the back of the stage. So we will talk in terms of downstage right, downstage left, upstage right, and upstage left. This is to clarify to all the people that doesn't work in the field, just to understand better. The proscenium is the part in front of downstage, so in front of the beginning of the stage from the audience side. So, okay, I can leave the word to Jason, and enjoy the webinar. Bye-bye.
Okay, thank you for clearing that up. Fedele, I think you'll need to unmute my video. Since I'm unable to turn it back on right now. Ah, there we go. Thank you. Hi, everyone. As they said, I'm Jason Romney, and I'm a professor at the University of North Carolina School of the Arts, and I am a theater sound designer. Before I get too much farther into it, I want to first apologize for any background noises you might hear coming around. Like many of you, I'm working from home right now, and my neighbor just decided to start mowing his lawn. So if you hear any of that, that's what's going on. So today I'm going to be talking about a concept called the precedence effect, or some folks call it the Haas effect. The term Haas effect is named after a researcher, Helmut Haas, who did some initial research into the effects of delay on stereo imaging. So let me demonstrate very quickly how that concept works. So let me share with you this demo I have, where you hopefully will be able to hear the effects. So this is a demonstration that I made in the program Max, or Max MSP from Cycling 74, that allows you to hear the effects of panning, both using traditional level and also delay. So first, I'm going to demonstrate the panning just using typical level panning, where we are controlling the volume of the left or right. So I'll do that first.
And
so right now you can see on the meters that we have the sound coming from both channels. And as I move the slider to the left, you can hear that the sound has moved to the left. And if I move to the right, you can hear that the sound has moved to the right. This is accomplished with level, and you can see that on the right channel we have sound on the meter, but on the left channel we don't. And that's what's helping us hear the difference in direction. I'm now going to do the same thing with delay. So I'm going to switch on the delay panning.
feeling wild and free.
So now I'm all the way over to the left. And depending on how you're listening, and if you have headphones on or something, you might be perceiving the sound mostly coming from the left, even though we have the same amount of sound coming from both channels. If I move over to the right, we get a similar effect.
I'd rather be sailing.
So what's happening here is instead of controlling the level between the left and the right, I'm instead controlling the delay. So when I delay the sound on the right channel, that means the left hits you first. And your brain interprets both sounds as though they are coming from the direction that came first. This is the Haas effect. And we are very sensitive to changes of direction with delay on the horizontal plane because of the way that our ears are mounted on our head. It didn't take very long for live sound designers to realize that we could take this concept and use it in a vertical orientation so that we could help control where the sound sounds like it's coming from. In a big stadium with tens of thousands of people, people aren't as worried about where the sound is coming from as long as it's generally the direction of the stage. In theater, however, usually the audience or the listeners are close enough to the stage that they can hear the actor's real voice propagating naturally through the theater to their ears. So if they hear that natural voice coming at them from the stage, and then they hear the amplified sound coming from a speaker up in the air up above them, that doesn't sound right to the audience. And when that's happening with multiple voices, they have a hard time knowing where the sound is coming from. They don't know who is singing, which person is doing the important thing. So we can use this concept of the Haas effect on a vertical plane against the actor and our sound system to control the delay so that the actor's natural voice arrives first. And we hear their natural voice first, and then we hear the sound coming from the sound system. And if you do this just right, the audience will perceive the sound that's coming from the sound system as though it were coming from the actor on stage. Now, there are a few rules that you have to make sure to follow when you do this. Let me pull that up and show you those rules. So first of all, the difference in time between the actor's voice and the sound system has to be within 5 milliseconds to 30 milliseconds. So if it's less than 5 milliseconds, then the comb filtering is enough that it might affect how the quality of the sound. But if you go to at least 5 milliseconds, though, usually the comb filtering has gotten dense enough that it's less problematic. And the difference in delay cannot be more than 30 milliseconds on average, or you will start to hear an echo. You'll perceive both sounds. But as long as the difference in time between the actor's voice and the sound system is within 5 to 30 milliseconds, then you should be able to perceive the sound as though it were coming from the actor. But you get the benefit of the extra volume or extra loudness with another rule, which is that the sound that is coming from each loudspeaker cannot be more than 10 decibels louder than the first sound, or you will start to perceive it coming from the loudspeaker, okay? And we'll talk about that. 10 decibels doesn't seem like much, but we will learn some tricks to get more than 10 decibels out of your sound system and still have it imaged to the performer. The third rule is that the sound coming from the sound system or the loudspeakers needs to sound very similar to the sound coming from the actor. And what I mean by that is if the sound that comes out of the speaker, the loudspeaker, sounds different, then we won't perceive it as though it's the same thing. So you have to be very careful about equalization. You have to be very careful about the placement of the microphone on the actor so that you're picking up the sound as clearly as possible, and that the frequency response of the loudspeakers and the sound system is as neutral as possible, so that what is coming from the loudspeaker sounds like what's coming from the actor. And if that works, then you will perceive all the sound as though it were coming from that actor. So before we move on to the next stage of this, I want to give the opportunity for anyone who might have questions so far. Any questions about anything that we've talked about so far?
No.
All right. So what we'll do now is I'm going to switch over to AutoCAD, and I'm going to show you an example of a sound system. And I'm going to show you how you can plan ahead in your sound system design to know how to accomplish this. So here is a AutoCAD drawing of a theater in cross section. So we're looking at it from the side. So this area is the stage here. And then we have a lower seating area. We sometimes call this the orchestra seating. And then we have a balcony seating area over here in the back. This is sort of a center cluster loudspeaker system. When you're trying to do precedence imaging, it's important that your sound system is primarily centered over the top of the stage, because we are very sensitive to sound coming at us from different directions on the side. But we're not as sensitive to the difference of sound coming from up above versus below. So when you design a sound system for precedence imaging, you want to make sure that the sound system and all the loudspeakers are lined up vertically in the same axis as the actor. So when I look at the actor here, I'm hearing sounds coming from this axis. They can be up above or from down below. But if the sound is coming from over to the left or right, then it's harder for this effect to work. So this is the center cluster, which is directly over the center of the stage. Now, I have a point here that is going to stand in for our actor or our talker. And I'm going to have that person sort of standing pretty close downstage, close to the audience. And then I have 4 seats that are labeled here. I have the front row of the lower seating area. I have the back row of the seating area, a lower seating area. And then I have the front and back row of the balcony. Now, to make this work, these rules of that 5 to 30 milliseconds of difference has to work for every seat in the theater. But it will take you the rest of your life if you actually do this math for every single seat. So the rules of thumb here are, if you can make it work in the front row and you can make it work in the back row, then usually it will work everywhere in between. So that's what I'm going to try to do, is I'm going to try to figure out how much delay I need to put on my center cluster so that the natural voice of the actor hits all 4 of these seats first. And then we hear the sound from the center cluster 5 to 30 milliseconds later. I'm going to use Excel spreadsheet to help me figure this out. And I'm going to first show you just how to build that from nothing. And then in the next step of this, I'll show you one that I've already created. So I'm going to create some columns here. This will be seat A, seat B, seat C, and seat D. And there's lots of information I need for these seats. I first want to know the talker distance. So this is the distance that the talker is from each of these seats. So we're going to go and measure this. Now, I'm going to be doing this in feet because sound travels almost a little bit more than 1,000 feet per second, which is about 1 foot per millisecond, which makes for the math very easy. You can do this in meters as well, but the numbers don't line up as equivalent like that. So I'll be doing it in feet, but you can do it in meters if that makes more sense to you. So let me start by just making this measurement. I'm just going to measure the distance here from the talker to seat A. And AutoCAD tells me that it is 18.25 feet. So I'm going to put that in here, 18.25. And now let's see how far our seat B is. So AutoCAD says 65.58 feet. Now I'll go up to the balcony. It says 53.99 feet for seat C. And back row balcony is 67.58. Okay, so that is the distance that the talker is from each of those seats. Now what I want to know is how long will it take for the sound of that talker's voice to get to each of those seats? So I'm going to call this talker time. To figure this out, I just have to convert the feet to milliseconds. And that, because sound travels approximately 1,130 feet per second, that is 1.13 feet per millisecond. So all I have to do is divide the distance by 1.13. So I will use a formula here in Excel, and I will say, take that value divided by 1.13, and I get 16.15. And I will copy that formula over to the other seats. And just to, so we don't have to look at such big numbers, let me make this to 2 decimal places. There we go. So the way that you know you've done this right is if the time value is a smaller number than the distance value. Okay, if the time number is slightly smaller than the distance, then you know you've converted it right. If the time value is a bigger number, then you did it backwards. So in this case, the sound will take 16 milliseconds to get to seat A, 58 milliseconds to get to seat B, 47, almost 48 milliseconds to get to seat C, and almost 60 milliseconds to get to seat D. Okay? So we now know at what time the sound from the talker gets to each of those listening locations. So now let's find out the same information for our sound system. So I will measure from my center cluster to seat A, and I get 25.56. So this will be center cluster distance, 25.56. And then to seat B is 55.56. To seat C is 41.33. And to seat D is 52.84. Okay, so now I just need to do the same thing and convert these distances to time. So this is center cluster time. And I'll do the same math. That divided by 1.13. And I will copy that formula over and make those numbers easier. Okay, so the center cluster takes 22, almost 23 milliseconds to get to seat A, 49 milliseconds to get to seat B, 36.5 milliseconds to get to seat C, and almost 47 milliseconds to get to seat D. So what I am interested in is what is the difference between those two sounds, because the audience will hear both the talker's voice and they will hear the loudspeaker's sound. And I want to know how much difference in time is that. So what I will do is I will take the center cluster time, minus the talker time. So we will say center cluster time minus talker time. And then I will copy that over. Now, I want all 4 of these numbers to be positive numbers between 5 and 30. If it's a negative number like this, in the back row of the balcony, right now I have a negative 13. That means that the center cluster is coming 13 milliseconds before the actor's voice is coming. And that's not what we want. We want the actor's voice to arrive first. So I will need to add delay to the center cluster loudspeaker. This can be done with any sort of like loudspeaker system processor, or sometimes you can do it in your mixing console if you can add that delay on an output or something. So I'm going to make a cell here for center cluster delay. I have 0 right now. And what I'll do is I'll edit this cell, and I will say center cluster time plus center cluster delay, and then I'll minus the front fills. Now, there's a little trick in Excel that you can do, and let me zoom in here and see if you can see this. So when I copy these, it doesn't move the delay value. If I put that little symbol in front of both the H and the 1, then it will know that I want to use this delay cell for every one of these when I copy it over. Okay, so now I'll copy that over, and now you can see that the C5 and the C3 are B5 and B3 and for this column, but the H1 stays the same. That way I can change it here and it changes everywhere. So if I look at these values, the worst situation is that minus 13. So I would like that minus 13 to be at least 5. So I can start by just adding 13 milliseconds of delay. And now I'm almost at 0. So I need to add 5 more, which I think would be about 18 milliseconds. I'm not quite to the 5, so I'm going to say 19 milliseconds. Okay, so if I add 19 milliseconds of delay, now all of these numbers are positive numbers between 5 and 30 milliseconds. So what this is telling us is at the front row in the lower seating, they hear the talker's voice first, and then 25 milliseconds later, they hear the sound from the center cluster. In the back row of the lower audience section, they hear the talker's voice first, and then 10 milliseconds later, they hear the sound from the center cluster. In the balcony front row, they hear the center cluster 7, almost 8 milliseconds after the talker. And in the back of the balcony, they hear 6 milliseconds later is when they hear the center cluster. Now, another little rule of thumb that I didn't mention before is that, remember I said that the center cluster could be 10 decibels louder than the talker in order for this to still work. That 10 decibels is really only possible when the difference in time is around 10 milliseconds. The farther you get away from 10 milliseconds, the less gain you'll be able to achieve without messing up the image. So this is a problem because I know that I'm only at the 10 milliseconds in that area at seat B, and I'm kind of close to it at seat C, but seat A and seat D are far away from that, which means I won't get as much gain and still have the image work at the front row orchestra and the back row balcony. The other problem I'm seeing here is, so this works, right? But what would happen if my talker moved? Right now, the talker is standing still, and with them standing still, I am on the edge of being able to make this work. So if the talker got closer, these numbers would change. If the talker got further away, if the talker moved upstage, these numbers would change, and I might get to a place where I was hearing an echo. If the talker moved closer to the audience, I would start to hear an echo at the front row. If the talker got farther upstage, then I would be less than 5 milliseconds of difference in time in the back of the balcony. So if all you're doing is a presentation where someone is talking at a lectern or a podium with a microphone and they don't move, then having a center cluster over the stage and you figure out this delay is probably enough. But in theater, our actors move, okay? They dance, they jump up and down, they move all around the stage, and we have to make this work no matter where they stand. So here, this requires a more complicated solution. We know that we can make this work if the actor doesn't move. So we need to add something to our sound system to allow for that. The reason that we have this big difference in time between the front row and the back row is because the location of my sound system is in a very different place than the location of my talker. So the distances are very different from the front row to the back row. So this is why we use front fills. So if you have worked with sound systems before in large spaces, you may have worked with front fills before. And the reason that we use front fills is, yes, because maybe we want to help fill in and put some extra sound in the front row. But in theater, when we're trying to create this precedence or Haas effect imaging, we use the front fills to help us with the imaging for everybody, which means I need this front fill to be heard all the way in the back row of the balcony. In order to do that, I need it to be far away from the front row. If the front fill is right here in the face of the person in the front row, then in order to make the back row hear it, it will be too loud for the person in front. So we usually like to have the front fill far away from the front row, as far as possible, so that we can shoot it to everywhere. So this front fill loudspeaker needs to be very omnidirectional. It needs to send sound everywhere. And we are going to put it here on the stage, as close to the stage as possible, so that it is in as close to the same place as the talker as it can be. So the front fill is not so much a front fill as much as it is a talker that doesn't move. So this front fill doesn't need to be very loud. It only needs to be as loud as the talker is. But because it doesn't move, we can use it as the reference point. So it turns out that when you are figuring out these delayed systems, you can have more than one loudspeaker hitting the listener, and as long as there is 5 to 30 milliseconds between each arrival, it still works. So I could have the talker arrive first, then 5 to 30 milliseconds later, I hear the front fill, and then 5 to 30 milliseconds after the front fill, I hear the center cluster. And even though now I'm hearing 3 different things, I will think all of that sound is coming from the talker, which arrived first. So to figure this out, I now have to figure out the distances involved for the front fill to each seat, but I also have to figure out where my actors can be. So I have found that usually you can make this work for about a 20-foot area on the stage. So I'm going to take my actor that's standing downstage here, and I'm going to make a copy that is 20 feet upstage. And I'm going to call this, let me copy these labels here. So this is going to be my downstage talker, and this will be my upstage talker. So if I can make this work for when the actor is standing downstage, and when they are standing in this upstage position, then it should work everywhere in between when they move around. So let me show you now another version of this spreadsheet. And I will make this spreadsheet available to you to play with if you want. Let me pull up the URL. So you can download this now if you want to. Go to cd-romney.com/downloads/precedence-demo_5-25-2020.xlsx. I'll leave that on the screen for a moment if you'd like to type that in. And then you can download that file and work with it for your own projects if you would like to. It has a lot of the math already set up for you, so you don't have to do a lot of that extra work. You could easily modify this spreadsheet for your own purposes for your sound systems as you change them and modify them. But this will save you a little bit of time. Normally, when I teach this subject to my own students, I don't give them this file because I want them to do the hard part and figure it out themselves. But for you, I will give you the shortcut. So let me show you what we have here. So the cells in green are the ones where you have to put information in. The cells in yellow are where you get the answers. So I have the downstage talker distance that I need to figure out. I have the upstage talker distance, the front fills distance, and the center cluster distance. So let's go in and get all of those now. So downstage talker distance, I'll just measure these all once more, 18.25 to seat A, 65.58 to seat B, 53.99 to seat C, 67.58 to seat D. And notice that those were automatically converted to time. Okay, let's do the upstage talker now. So upstage talker goes 38.04 to seat A, 85.43 to seat B, 73.36 to seat C, and 86.68 to seat D. And those were automatically converted to time. Now I need my front fill distance. So front fill to seat A is 13.92. To seat B is 62.64. To seat C is 52.09. And to seat D is 65.92. And those were converted to time. And now let's measure the center cluster again. I don't think it moved, but just in case, let's try again. 26.56 to seat A, 55.56 to seat B, 41.33 to seat C, and 52.84 to seat D. All right, so now all we have to do is add the delays. So these two rows here are the front fill minus the downstage talker. And the next one is front fill minus the upstage talker. And you can look at the cell here that I've already added the front fill delay value into that. So if I look at these four, what is the worst one? The worst one is this, negative 21.35. I need that to be at least 5. So I'm going to say 26 milliseconds of delay on the front fill. And that gets us to 4.65, so I'll say 27 milliseconds. So 27 milliseconds on the front fill means that this one is now 5.65, and then the largest number is back here in the balcony at 25.53. That's okay, right? So all four of these now are between 5 and 30 milliseconds. So that will work. Now in the center cluster, what I'm doing is I'm comparing center cluster minus front fills, because now that the front fills are time aligned appropriately with the talkers, I don't have to worry anymore about the time between the center cluster and the talkers. All I have to do is think about the center cluster relative to the front fills, because the front fill is now the latest arrival to the listener. And I want the center cluster to arrive after the front fill, 5 to 30 milliseconds. So the worst one is 38 milliseconds, 38.5 milliseconds. That's the worst number. I need that to be at least 5. So I'm going to say 43 milliseconds on the center cluster. Gets me almost there. I'll say 44 instead. So now I'm at 5 milliseconds in the back row balcony, 28 milliseconds at the front row. Now, what you might be thinking now is if you're putting 44 milliseconds of delay on the center cluster, there is more than 30 milliseconds difference between the talker and the center cluster. And yes, that is true. But because the front fills are there, the front fills bridge that gap in time so that you don't hear the echo. So when you hear the center cluster images to the front fill, and the front fill images to the actor. And so all of the sound will sound like it's coming from the actor, even though you're hearing it from a front fill and a center cluster, and the center cluster is more than 30 milliseconds. So that is the basic idea of how to figure this out. Now, if you have a very large theater and maybe it's a big balcony and you need to put loudspeakers under the balcony to fill in the back row, that becomes a fourth arrival, and you could add that to the spreadsheet as a under balcony distance, under balcony time, and then you would subtract the under balcony time from the center cluster time to figure out how much delay to put on the under balconies so that they arrive after the center cluster within 5 to 30 milliseconds. You could do the same thing for balcony fills if you needed those. And you could continue adding loudspeakers all the way back as far as you want, as long as every arrival gets to the listener within 5 to 30 milliseconds of the one before. So that is a very quick demonstration of how this works. I'll now take questions. If anyone has any questions, I'm happy to answer them.
On Zoom, there are not questions.
Anything from Facebook or YouTube?
No. Zoom?
There isn't.
No.
No, it's all good on Facebook
Okay.
and YouTube.
So let me put into the. I hope you were able to copy that link. If not, I will put it into the chat on Zoom, and then others can share that link to that spreadsheet. That will hopefully help you. Let me show you just a couple more features of that I didn't talk about. So one is that you can see over here that you can, like if you want to figure this out in meters, that's fine. You just need to change the speed of sound here. So I have the speed of sound here as 1,130 feet per second. If you wanted to put that in meters, I believe it's 344 meters per second. You could put that in there, and it will convert that to whatever, figure out what number you would use to convert the time. And as long as you enter meters in all of these other cells for distance, then it should still work. All the math should still work. So you can do that. And again, if you wanted to add delay fills for under balcony or balcony delays, you can add them here and add your own cells for delays on that point. So hopefully that's helpful. If you would like to get a copy of the delay panner demo that I shared, you can get that on one of my websites, which is digitalsoundandmusic.com. This is a page for a book that I contributed to. And if you go to this curriculum link and go to Learning Supplements.
Sorry, Jason, there is a question. There's a question from Zoom.
Great.
Ras asks, what about the COM problem with separate source in space and time?
Can you say that one more time? I'm not sure I understand the question. Oh, comb filtering. Yes.
Comb filtering.
Yes. Okay. So yes, good question. So here, this will create comb filtering. As you know, if you have two sounds that arrive at you that are the same but at a different time, comb filtering will happen, and that creates some cancellations and reinforcements in the frequency response. So yes, that will happen. But here is the important thing to know about comb filtering. Every sound that we have ever heard in our entire life has been comb filtered because we are always hearing sounds reflected off of surfaces and coming back to us at a different time. And when that happens, comb filtering occurs. We only notice the comb filtering when the difference in time is very small. And that's why we want to have at least 5 milliseconds, because when the time becomes more than 5 milliseconds, then the comb filtering becomes so much and so dense that those cancellations, the peaks and notches in the frequency response get so close together that it enters what is called the critical bandwidth of our hearing. So our hearing has developed what I call a blind spot. It's a part of the sound that we don't hear well. And that is, if there are big changes in level on the frequencies within a certain range, and on average, that's like 1/3 of an octave, then we don't notice the comb filtering as much. Basically, our brain says, that is so bad, it can't possibly be right. Therefore, we'll fix it, right? And that's the only way that we are able to survive every day, because we hear sound reflecting off of things all the time and comb filters all the time. So our hearing has learned to ignore comb filtering that is a result of delays of time that are very large. It's only the small delays that we notice. So that's why you need at least 5 milliseconds. If less than 5 milliseconds, yes, you will hear comb filtering and it will not be good. But more than 5 milliseconds, it's okay. Any other questions?
Yeah, the opposite of that then, at what point would you say is the limit before we hear what sounds like an echo or a discrete reflection?
Yeah, so it depends. It depends on the sound. If it's a drum, like somebody hitting a snare drum, maybe 20 milliseconds at the most. At 20 milliseconds, you would start to hear echo. If it's a voice, like a person singing or talking, I have found you can usually go up to 30 milliseconds. But after 30 milliseconds, you'll start to hear the echo. So that's why the rule of 5 to 30 milliseconds. The 5 milliseconds means the comb filtering isn't bad. The 30 milliseconds means you don't hear echo.
Okay.
Okay.
Other questions?
No. Any question in Zoom?
Okay, so while we're waiting for questions, let me show you where you can get that delay demonstration. So on the website, digitalsoundandmusic.com, go to Learning Supplements. And many of these are great, but if you go to Max Demos, there's one for the delay panner. And you can download, you can download that. You will need to also download Max MSP, the Max software, but it's free demo to run it. And there's a link here to download that. And you can then use that if you want to play around with this, or use that demo if you want to try to teach this concept to other people. You can use that demo as well. Any other questions?
Fidel just said for me to just share an experience I have that is maybe slightly off with your time difference. So in February, I was in Dallas, and I was asked that I want to go to a mega church, and I said, yeah, sure, why not? So it's a chance to hear a different sound system, a different type of acoustic environment. But what I noticed was that when I got there, it was 1,500 capacity, but it was very dead, acoustically dead. And we were sat maybe 5 meters from the front. There was no lip fills. The only speakers were in the hangs, and they were quite high. So I'd guess that they were maybe 7 meters up the bottom of the hang. But what was interesting was when the band was playing, it sounded good, sounded clean. But when they brought out the pastor to speak, where it was just vocal, just dialogue, no real reverb to mask any reflections, and no music to mask, there was a very definite echo that I could hear. It was actually very distracting. But trying to work it out, I would guess it was around maybe 15 milliseconds. So yeah, do you think that the reverb maybe has an impact on that?
A little bit. So let me go back to the spreadsheet and show you something. If you remember back when we did the first example, it was in the front row that we had the largest amount of difference in time, which was 25 milliseconds. And so if all you have is the loudspeaker system up above the stage and no front fills, then the people in the front row, if you are delaying your center cluster to try to make this work, then the people in the front row are likely to hear echo, because the difference in distance is very dramatic for them. The difference in distance between the center cluster and the talker for the people in the back is very similar. The distance is similar, so it's easy to make it work there. But in the front row, it's very, very difficult. So that's all the more reason why you need the front fill, because if you had the front fill, it could bridge that gap, right, between the ones up above and the talker. Now, certainly reverb can help. I found that what tends to happen when you get this right, when you get this to work, you're sitting in the audience and you're hearing all of this sound, and if the delays are all right, then you think it's all coming from this actor, but the actor is far away, but it sounds like the actor is closer to you than your eyes think that they are, right? And so what I find that the reverb helps with is the reverb helps to create the sense that the actor is farther away, right? You hear the room better. And I will usually hang a separate sound system for that. So I'll have different loudspeakers that do the reverb so that the reverb comes at me from a different direction. And I find that it helps to get the sense of the actor being as far away as they are. I have not found that reverb is very helpful with if you're hearing an echo, right, to mask it. But what I have found is that if you don't delay your reverb as much as you've delayed the dry sound, then you can undo all the work you've done, right? So if the reverb hits the audience first, and then you have the dry sound, it doesn't make any sense, right? It's like nothing you're hearing makes sense. So you have to delay the reverb, or it doesn't work. So I suspect what was happening in your experience at the church was because you were so close to the stage, there was such a big difference between the center cluster above and the talker. And if the talker was, particularly if the talker was close to you, then you would hear that echo. Whereas the band who was farther away was within that 5 to 30 millisecond range. I suspect that was probably the problem.
The talker was probably somewhere in the region of 15 milliseconds earlier arriving than the PA.
Yeah. So it could have been that it was 15 milliseconds. So it could be that it was 15 milliseconds out of the precedent zone. But if it was actually 15 milliseconds between it, you also have to think about the difference, right? Because if the center cluster is like right above your head, it's harder for you to put these two things together, right? Because there is such a big difference between them. There has been some research that I've read that says there's an angle, vertical angle where this works. You know, and it's like about, I don't know, 20 or 30 degrees. And if the difference in location between the sound on the stage and the sound in the air is more than about 30 or 40 degrees, then you will start to drift your perception up to the thing that's up above. So it could be that was part of the problem as well, is that it was just too far up above your head for your brain to pull these things together. All the more reason to have the front fills on the edge of the stage to kind of help bridge that.
Sorry, there is Dunstan that is reporting Alton Everest Master Handbook of Acoustic has a good chart showing the relationship between delay time and the level and how those are perceived by the listener. Okay, and there is a question by Paul Lozada directly to you, Jason. Have you made the measurement that support the calculation you show? And if so, what is the recommended method of evaluating the Haas effect in large space?
Okay, good. I was hoping somebody would ask this question. So I don't have time to answer this in great detail, but I did anticipate this question, so I did prepare a little bit. So this is a saved file from the software Fuzz Measure Pro, which is an acoustic analysis software. What I have done here is these are actual measurements that I captured from a real sound system that I did. So what I do is I put microphones in the different places that you need to put them in. So I had a microphone in the front row, a microphone in the back row, a microphone in the front of the balcony, a microphone in the back of the balcony. And I think I had a total of 6 microphones in this particular setup at different places in the theater. And what I did is I sent sound out of the system and measured the time for just the front fills. So each of these FF1, 2, 3, 4, 5, 6 are the impulse responses of when the front fills got to each of those microphones. Then I have the center cluster. When did the center cluster get to each of those? And then I had some delay fills like under balconies that I also measured. I measured these all separately. And then what you do is you just superimpose them. So if I select the front fill one and the center cluster one, this is the difference in time between when the front fill got to the front row and the center cluster got to the front row. And you can see that it's about 56 milliseconds on the front row and 73 milliseconds for the center cluster. So, you know, it looks like it's approximately 15 milliseconds of difference. That works. The front fill came first. I could take the microphone number 5, verify that, and that looks like it's about 11 milliseconds difference. The front fill is coming first. But you can also add in the delay fill. So here's my delay fill in the orange, and you can see that I have the front fill coming first, then 11 milliseconds later is the center cluster, and then it looks like 10, 20, about 22 milliseconds after the center cluster, my delay fills show up. So that's how I verify this. Now, this is obviously after I added the delay to everything. So when you superimpose the impulse response on top of each other, you can see the difference in arrival. You can add delay to something, remeasure, and look at it again, and see the difference in time to verify that you've done it correctly. And then you just have to listen. You listen and adjust the level of everything to get it to work.
Okay, in Zoom, there are any questions? So if you want to go.
Sorry, I have one more question. I'm not even going to attempt to pronounce that name. Is it possible to transfer these indications in a left-right system for center front fill?
Yes, but it's more difficult because we are very, very sensitive to sound coming from different directions this way, right? Because of our ears are mounted that way. So the difference between sound coming from here and sound coming from over here, that's easy for us to tell, right? We can figure that out very easily. Sound coming from here versus here, harder for us to figure that out, right? Because in both cases, that sound hits the two ears at the same time. So if you wanted to do it with a left-right, it is possible, but it will be more difficult because even if you get the time just right, you still have to overcome the sensitivity. And remember, as the audience moves, they'll go over here, and they now are much closer to this one on the side, which will mess up the time, right? So that's why if you do a center system, it works better, because then when the audience moves, their difference in relationship in distance from the sound system doesn't change. And so it works. But if so to make that work, you would have to look at, you would have to measure distances to the side sections of seats and do many more calculations to try to get the timing to work right. So it's possible, but very difficult.
That's all from Facebook.
No. On Zoom, there are not questions.
Okay. Thanks, Jason, for your experience.
Yes. Well, you're welcome.
A very interesting, beautiful moment. Thanks for your time. The teacher with the smile. Thanks. So, thanks to all. Thanks to Jason. Thanks to the moderators, Alberto Bonardi, Gianluigi Ferroni, e Abeshil. See you the next time. Thanks to all. Bye-bye.
Bye.
Bye. Thanks, everybody.
Bye, Jason.
Bye, everybody.